Hello and welcome to section 3.2 in our linear algebra notes. Today we're going to understand the impact of row reduction on determinants. We're going to use row reduction to compute determinants, and we'll also compute the determinant of a transpose of a matrix and the product of two matrices. So first of all, if we take, what we're going to do is we're going to develop some of these properties just by looking at generic matrices in the 2x2, and it turns out that the properties that we'll see will generalize to larger matrices as well. So if we take the determinant of just an arbitrary matrix, A, B, C, D, well, we multiply the A and the D, and then we subtract out the B times C. Now, if we swap the top and bottom row, this would be a row swapping operation. We end up with CD on top, AB on bottom, and then when we take our determinant, we get, BC minus A times D, which in fact equals negative times the determinant of A. And that's going to be true in general. Let's look now at what happens if we multiply, this is your first quiz. Try multiplying one of the rows. So for example, you could take the top row and you'd get a constant times A, that same constant times B, and we're only multiplying the top row by that. And I want you to go ahead and compute that determinant and see what you get. Okay, so now let's go back to our original matrix A, and let's add a multiple of one row to another. So let's do R2 plus some constant times R1, just to keep it pretty general. So we keep our R1 the same, and then our R2, and our first column is C plus K times A, and our second column is D plus K times B. Well, when we take that determinant, so let me go ahead and erase that. So we've done our row operation, and we want that determinant. So we have A times D plus KB minus B times C plus KA. When we distribute that A, and remember, since real numbers are multiplication commutes, we can reorder those entries. So this BKA is the same thing as, and we have to distribute our sign as well, KAB. But then you can see those two cancel each other out, and we're left with AD minus BC, which is in fact the determinant of our original matrix A. Okay, so now we've seen several different row operations, and so the row swapping we saw multiplies the determinant by -1, and that's going to be true in general. The scaling by K on one row multiplies the determinant by K. So if you scaled both of those rows by K, you'd end up multiplying by K squared. And then finally, the row replacement operation, that's the one where you add a multiple of one row to another. Row replacement. It has no impact on the determinant, so no change to the determinant. Okay. So now we say a matrix is upper triangular if all the entries below the main diagonal are zeros. So what you do, remember your main diagonal is those entries, kind of heading down in the diagonal, and then you look at all the ones below it, and so in this case they're all 0 for A, and so A is one of the answers to our quiz. And then look at the other ones and see which others have all zeros below the main diagonal. Okay, now we're going to compute determinants of each of these matrices, and let's go ahead and use our expansion method, our cofactor method, at least for this first one. So we take let's see, so the determinant of A, well, that 1 has a positive sign in front of it. And then sometimes we write the determinant with kind of absolute value signs. And that further becomes 6 times negative 3 minus 2 times 0. And so really we get negative 18. Just to change it up a little bit, let's do B with the with our little crisscross method. So recall what we do there is we write the columns of B, the first 2 columns. Oops, I want to make that pink. Let's see here. We take the first 2 columns of B and we tack them on to the end. And then we do a little crisscross. So we have this diagonal, which is 0. Oh, this one's 0 and that one's 0. So we get a 0 plus 0 plus 0 and then minus, and now we go the other way. We have that 4 times 6 times 3 and then 0 and 0. And what you should start to notice, so this is that 4 times that 6 times that 3, but it just has a negative sign attached to it. So let's see, that would be, I think that's 92, negative 92. No, sorry, 24 times 3 is negative 72. Okay. Let's look at, oh, and actually, before I go further, you should notice we had that 1, and then the 6, and then the negative 3. If you look at C, and again, you can do it whichever way you want. Let's do one more with that kind of diagonal situation where we just rewrite things. Actually, I guess this one would be a little easier to see cofactor wise. Let's do it that way. So we go down that first column. So we have a 0 times the determinant of 2, 4, 0, 2 minus 0 times the determinant of 4, 6, 0, 2 and then another plus. Remember we do checkerboard. 4, 6, 2, 4, and those are all 0, which again you should notice is down that main diagonal. So we had one on the off diagonal because that is, I guess, if you look at the pattern, it kind of has zeros below the off diagonal, but we subtracted it instead of adding it. And then finally, the determinant of D. Let's do that with the crisscross again, so we can get one more crisscross example. So remember, we rewrite the first 2 columns, and then we multiply down the diagonals. So 4 times 2 is 8, times 5 is 40, plus, and then we have a couple of things with zeros. And then going the other way, 1 times 2 times 0, 2 times 0 times 4, and 5 times 3 times 0. So minus 0 plus 0 plus 0 equals 40. And so in general, if A is UT, which is our typical abbreviation for upper triangular, well then its determinant is just the product of the diagonal entries. Okay, so now we're asked to do some row reduction. And so let's go ahead and I'll try to do this relatively quickly. So it asks us to get it to reduced echelon form, but without doing a lot of scaling. So let's do row 2 minus row 1. And so we get a 3, 4, negative 3, negative 1. That stays the same. And then we get a 0, negative 4, 1 minus negative 3, negative 3 minus negative 1. And let's go ahead and combine some operations together to save time. So we can do row 3 plus 2 row 1. And so that gives us 0, 8, negative 4 minus 6 is negative 10, and 5. And then our last row. And let's do a little bit more. So far all we've done is row swaps. Let's do row 4 minus 2 row 1. So that's 0, 0. Negative 4 plus 6 is 2. Negative 1 plus 1 is 0. And then let's also take row 3 plus 2 row 2. So we get, I believe this is correct. And then finally, we want to get that 2 in the bottom row to go away. So we do row 4 plus row 3. And so row 4 becomes a 1. And now we have our matrix in echelon form. It's not reduced echelon form. That's all we really need, because now we can use that formula that we talked about just above to compute the determinant. So now the determinant of u, so this is our u here, just equals 3 times negative 4 times negative 2 times 1. And so that just equals 24. I just did the quiz for you. That's okay. We'll make this the quiz. So here's our quiz problem. Now we want to know the determinant of A without doing any work. And so notice that we only use the replacement operations. So go ahead and fill in what is the determinant of A. Okay, and so our last page, we're going to talk a little bit about what happens when we multiply matrices and what happens when we take transpose. When we take the transpose. So the determinant of A is just going to be 3 times 1 minus 6 times 0, which equals 3. But you should notice that even if we take its transpose, so our main diagonal stays the same and the other stuff flips off of it, well, at least in the 2 by 2 case, we get the same basic thing. And in fact, that's true in general. The determinant of a matrix is always just equal to the determinant of its transpose. Okay, so this is always true, not just 2 by 2s. And now let's do, okay, this is our quiz, so I'll try not to do this one for you. Compute the determinant of B and the determinant of A. So the B is still the same B up above. And see which of these 3 situations is happening.